Hello, everybody. So today I wanted to just touch on the subject of a ball end cutter for woodworking. I got a push from a viewer who wrote in a question that I read this morning asking about the cutter that I was using in the one-to-one duplicating machine, which here's a link to that, or maybe over here. And he was asking about this cutter, which I probably should have explained at the time, but nevertheless, here it is. It's a funny kind of cutter that probably most of you have not seen before. I think of it as two whirling spoons. We're going to look at these last, and we'll look at the alternatives first, okay? First of all, if you ask most people what a good round end cutter would be for woodworking, most people would steer you towards these kind of bits. These are cemented carbide that are brazed to steel shanks. They're usually called Corebox bits. So a Corebox bit is from old language from pattern making. And sometimes people think of it just as a semicircle, but it's also apparently the name of the bits when it has this cylindrical portion as well, right? So some Corebox bits just look like that, and some of them look like this one, or yeah, all of these. If we look at a quick review of our tool geometry days, which we could go back and look at that. If this is a cutter that's cutting wood in this direction, then this angle here that's in the center is called the sharpness angle, and that's the actual part of the tool. That's the tool, right? And then the angle that this surface of the tool makes with a 90-degree line is called rake, okay? And almost all woodworking tools need rake in order to work very well. There are some exceptions. And then on the other side of the sharpness angle, measured from the horizontal, is clearance. And we need clearance in order to get the sharpness angle to penetrate the material and, begin to take a cut into the wood. When we look at these cutters, we can see that if you measure this angle of this cutting surface, then you'll see that this is a radius here, which means in effect we have zero rake. So the sharpness angle is very robust, and this is a tough, hard, long-wearing edge. It'll last a long time, but it doesn't have any rake at all. And this means that we'll have high horsepower demands, high heat, and not that great a cut compared to cutters that would have rake. So this is a scraping cut, a true scraping cut with 0 degrees rake, right? And then you can, well, this cutter isn't any different. Also 0 degrees rake. If we look at this little cutter, because they've made this in a different way, if we notice this is two pieces of cemented carbide that meet at the center where there's, actually it looks like almost no material there in the center where these two pieces touch. This tool is made with one plate of cemented carbide that's right down the middle. And as a matter of fact, that means that we have on this tool, at least on the side, we have negative rake. The angle of the cutting face has opened in this direction relative to the radius, and it's given us not just 0 rake, but actually negative rake, a little bit of negative rake. And that's also a scraping cut and will make even more heat and take up more horsepower. Now, the heat and horsepower thing, you may think I'm making a big deal out of nothing, which you could say that because we have routers that spin these things at 30,000 RPM. The edge kind of disappears at that speed, and they actually work pretty well and leave a pretty good surface. But let's look at what happens at the bottom of the tool, right? Because that's a whole different story. So if we're using a tool like this to cut a surface that has a curvature to it, then we're going to end up leaving the surface cut by this center of the tool, not by the sides of the tool. Even though the sides of the tool may take away some material as it's roughing out, in the end, the only surface that we're going to see on the finished part is right down here at the end. And as everybody knows, in the center of this tool, the molecule in the center is just spinning around. It's not actually moving at all. So no matter how fast you're spinning this tool and how fast the periphery of the tool is going, the center of the tool is not moving at all and just kind of twirling around in a manner that can't be considered cutting, but is actually just pushing. So this is not really a woodworking tool at the end, even though it does cut wood. All right, so just for fun, we're going to look at metalworking tools. Here's one. Oh, this one happens to be left-handed. But anyway, here's a 1/2-inch ball cutter. I think you might be able to see that there is no way that this can cut in the center. It can't. It can only push on the material. And if you have a rigid machine, this is solid carbide, very rigid tool. If you have a rigid machine with this solid cutter and a soft material, especially like aluminum, it'll just kind of push the aluminum out of the way and leave a pretty good surface. But it's not really cutting. It's kind of just pushing the material. Now, this cutter is a 3-flute cutter. And I don't know if you can see, but one of the flutes is longer than the other two and extends all the way into the center. So they're at least trying to pretend that there's some kind of cutting going on there. But I promise you, it's still pushing and scraping, not really cutting, not slicing. In 1992, when we were getting ready to start up the Parker Guitar Factory, I called Bob Taylor and said, "Hey, Bob, how do you start a guitar company?" And he said, "Well, if you come out here, I'll be happy to show you what we've done." So at the end of 1992, I got out to Southern California and spent a day with Bob Taylor, asked him a million questions, and got to talk to his employees and try and figure out how they'd gone about it and how they'd solved their problems. Very useful to me at the time, I assure you. Anyway, we got talking about cutter geometry because they were using their CNC machines to cut necks for flat top guitars, which of course have all kinds of curves and the heel shape and blah, blah, blah. And so I asked him about his cutter geometry, and he said that he'd been working with the Kennametal company, and the Kennametal guys and Bob Taylor worked together, and they figured out that 12 degrees was about the right amount of end clearance for such a ball mill. So I called the president of Kennametal and to order some tools, and he laughed and he said, "I can't believe you guys are all talking to each other." He said, "We serve a lot of industries and everybody else is trying to slit each other's throats." And I said, "Well, nobody ever mistook guitar making for a get-rich-quick scheme, so we're all trying to help each other out." Anyway, thanks, Bob. So we ordered the Kennametal tools, which were something like this 3-flute tool, as I recall, with 12 degrees end clearance. And I wasn't very happy with how the tools worked. And so what I chose to do was to buy a high-speed steel tool. We needed a longer tool than this, so this is a 2-inch length of cut. I ordered them with square ends, and I ended up grinding the end by myself, by hand. Here's 3 of these tools from, this is ancient history from Parker Guitar Production. And I ended up using a lot more than 13 degrees end clearance and, played around with the surfaces and angles at the end of this cutter to try and get the best surface possible. And it worked pretty well, but it still was fuzzy because, as we all know, at the end of the tool, nothing is really happening in terms of surface speed. If you look at what happens right here, there's no motion. This might be going 5,000 surface feet per minute, but this is not. This is going 0. What happens is if you take the tool and you tip it like this, then the bottom of the cut ends up being over here somewhere, depending on how much you tip it. And this is moving. And you can get some real cutting and surface finish from this part of the tool. And this is why people have 5-axis machines, 4 and 5-axis machines, so that you can tilt the spindle in some cases so that you can get the ball end tool to work better, and the part that doesn't work is over here where it doesn't matter. And the part over here where it matters is actually spinning quite a lot. So that's a big improvement. For most of us, that's not really an option, although I will point out that instead of moving the head of the machine, you could move the tooling. In other words, you could make a fixture plate like this and hold your tooling at an angle and then run your program with a cutter that was coming in this direction and get the same benefit, if that makes sense. Get the same benefit of cutting off axis and utilizing the surface speed of the cutter at this diameter. Here I'm going to show a couple of other things. These are burrs. These are ground by hand, believe it or not. All these teeth by some very skillful people. These work pretty well, removing small amounts of wood, especially for hand-guided operations. The Severance Tool company is really the best at making these, and we'll provide a link if you think you need something like this that's hand-guided in your shop. A burr is often a good choice. And the reason that it works and this won't work safely is that the shape of this tool means that it could dig in and do something, grab the work and it could get away from you. Whereas guiding a router by hand with a tool like this in it, because the teeth are close together, it actually works out so that it's pretty easy to guide and use. Can get some good results like that. Even a bigger one than this would be helpful sometimes for shaping. On the renewable insert side of things, we have this kind of tool which suffers from the same problem as this one that we just spoke of, where the insert is right down the middle. And so what that means is that whereas this would be 0 rake here, actually what we have is negative rake. In other words, that would be 0, but because of the thickness of this part, cutting tool, the rake angle on the periphery at least is a negative rake angle. So again, just to be clear, this is positive rake, and this would be negative rake on this side. So actually the tool is way over here. And so this is, if this is a scraping cut, this is even less good than a scraping cut, and even less advantage when trying to cut some wooden fibers. Okay, so enter some very clever tooling designed by somebody in the Salstrom family in the early part of the 20th century. These cutters were designed for use on multiple spindle machines that were all the rage back then in manufacturing. Gibson Guitars had a bunch of them that they carved archtop plates and then Les Paul bodies and necks and everything that needed carving at Gibson was done on a Salstrom carving machine. And we'll provide a link to the company history and some photographs of these incredible machines. These incredible machines, which still, part for part, could beat a CNC machine hands down, depending on how much accuracy you need. But at any rate, these guys, as you can see, are wicked little spoons that whirl around and actually cut wood. So this has a hysterical amount of rake. So this would be 0 rake, and you can see this has so much rake, just an amazing amount of rake. Plenty of clearance to do the job. They're just fantastic. These cutters are made out of M42 steel, very tough and hard and long wearing. The cutters are quite a number of pieces. So we have the shank or arbor, and there's a little roll pin here. And here's a conical surface that the blades bed down to, each to a side. And then the little pin keeps the things from moving around. And then finally, there's this left-handed thread for a right-handed cutter. More on that in a minute. Left-handed thread that has a conical surface on the inside that matches this taper, and we can go down there and kind of hold it all together at speed. And these things were great. I've never had any trouble with them. I've had these cutters for 20 years, and I've just discovered that the gentleman who made these cutters, Philip Salstrom, is still in business, and we will provide a link and his contact information in case you want to get one of these cutters for yourself. Now, we were saying that these kind of round-ended cutters don't cut at all in the center. Well, you can see there is no center to this cutter. The cutting is done by these blades out here, which I assure you cut very, very well. You can see this has a small shank, a 1/4-inch shank, compared to these other 1/2-inch shanks here on these tools we've been looking at, partly because this needs very, very little power and will operate really smoothly and not burn anything. I can't tell you what a gigantic difference there is between a tool like this and a tool like this for a material like wood. It just is, there is pretty much no comparison. This is kind of brutality, this sort of beating the wood off with a sledgehammer or something. And this is an elegant slicing tool. They call this a rougher, but that's only because it's able to take off a lot of material at once without a lot of horsepower. So these machines were often many spindles running at once. The operator would be at the center of this machine with a series of spindles, say 12 spindles on the right side of the machine, turning right-handed, and 12 spindles on the left side of the machine, turning left-handed, with a pattern in the center and 12 work pieces on each side. And this way, when the operator was just paying attention to following the pattern in the center, and then 24 parts were being made, whether they were guitar necks or table legs, or during both World Wars, of course, gun stocks for infantrymen. And in fact, the Salstrom machines are sometimes referred to as gun stock lathes because one aspect of this machine allows it to rotate the pattern and all of the parts to be cut precisely the same angular relationship and change that angular relationship, thereby making it kind of a 4th axis machine so that you could load a piece of wood and then by rotating it, gain access to every surface on the part so that you could cut any part of that piece of stock. That's my plug for the Salstrom cutter, and Philip Salstrom is keeping up the tradition of his family by providing this for us. I'm not sure exactly what these cost right now, probably less than $50, worth every penny. You'll find him a delightful guy to deal with if you contact him for one of these tools, of which no one else ever made, apparently, and are not available anywhere else. So there it is. It's my gift to you, the Salstrom rougher. Hey, everybody. I thought this might be a time to just have a brief look at the two kinds of materials that we normally use for cutters and explain the differences and advantages of each one, since I think it isn't maybe widely understood exactly how this stuff works. Say for a chisel, we have a tool steel, which is alloyed with a variety of little ingredients that, a very specific recipe that helps us with an edge that can hang in there for a long time, get really sharp, and serve well for hand tools like chisels, planes, knives, and things like that that we all use to build instruments. When you move to a rotary cutting tool that's powered by an electric motor, then we have new concerns about the material and new requirements in order to make sure that we're using the right material for the job. So what happens is, if we were to use the same tool steel, which is, no slouch, that we use for chisels, and O1 tool steel would be some kind of example of that, a very favorable alloy that serves lots of different purposes. O1 stands for oil hardening. If we used O1 for a cutting tool like this, for example, it would be easy for us to run it fast enough and work it hard enough for it to get so hot that it spoiled the temper. And so that's a problem, that regular tool steels, can get so hot that they become softened by temperatures as low as, say, even 450 or 600 degrees Fahrenheit. Can take the temper out of a steel. And I know that when we're grinding our chisels, of course, the color of death is purple. If you burn the corner of your chisel purple, you've spoiled the hardness of the steel, and you've softened the edge in a way that is really bad for the tool and won't let it work the way it was designed to work. So around 1900, a bunch of engineers in Bethlehem Steel got together and started playing around with alloys, creating them and subjecting them to much, much higher temperatures than regular tool steel, such as O1. And the alloys that came out of this that were used starting in the early part of the 20th century came to be known as high-speed steel. And we've all seen these in our tool catalogs and whatnot. When you buy drill bits, they're called high-speed steel, certainly. And what it really means is high heat. And it's called high speed, which means you can run the tool spinning at high RPM and making it cut aggressively. The tool can get quite hot. In fact, some tools can withstand even being red hot. And obviously, you need some horsepower and a tough material to get a tool up to being red hot. It's very common for a piece of tool steel to be able to work at that temperature. I don't know, in the last 100 years or so, a lot of precise alloying and experiments have produced darn cheap, high-speed steel that is easy to work with, easy to get super sharp, and will withstand tons of heat. So anyway, high-speed steel, very nice material, and especially useful for powered cutting. Carbide was first used in the mid-30s, I guess, something like that, although it didn't work as well as it does now, certainly. Everybody knows about carbide now. Router bits are carbide, saws are carbide, sometimes called cemented carbide, because it's a ceramic material that's cemented together with a little metal. And then, say in the case of a saw or a cutter like this, the carbide is made in plates or sheets, and then it's cut up into pieces and then bonded with braze, high temperature braze material, and then ground after after the tool is assembled. So carbide has a lot of advantages. It's even harder than high-speed steel, and is very, very abrasion resistant, which is great, particularly when things are going fast and heating up. As we all know, router bits are almost all carbide, and they're almost all made like this, where the shank of the tool and the body of the tool is made of steel, and then the carbide is brazed on. Since it's made in molds, you can fairly economically make these cute little shapes out of cemented carbide that have built-in features that don't need to be ground, such as this one, or these are some examples of carbide inserts which go into a tool like this, say, or like this, that physically clamp the insert to the steel body of the tool, and are replaceable when they wear out. And this, for a long time, was just part of metalworking, but now we have cutter heads and tools in the wood shop that have replaceable carbide teeth in them, or cutters as well. At any rate, one of the things that's a problem with the cemented carbide is that because of the way it's made and what it's made of, it's quite brittle. It doesn't like to be shocked. When it sees an impact, it tends to crack and fail by chipping. So that's one of the problems with cemented carbide. And the other problem is that unless you do something special and you're very careful, it's very difficult to get a thin, low angle sharpness angle. And you can see that these cutters, what is that, a 45-degree sharpness angle, but most of them are not. Most of them are much greater than that. And this would be a heavy-duty turning insert designed to make a lot of parts. You can see it's got a cutting surface on both sides of it, identical. And these, again, made in molds and designed to see huge cutting forces, lots of heat, the kind of things that happen, more in metalworking, but still in woodworking, the carbide is used in cutting tools like this and this because it's very difficult to get it dull in wood. It's really hard to dull carbide in wood because wood is so soft by comparison. Now, that's great, and it's the reason that every other thing is made out of carbide now in the wood tool catalogs. But I will tell you that because carbide cannot normally be brought to a thin or low sharpness angle, often it's not a very good cutter for wood, which is kind of what the whole tool explanation here is about the ball end mill. So I've been talking about rake, Here's a funny carbide router bit that I offer as an exceptional example of a tool with quite a lot of rake. Now this has, oh, I don't know, 25 degrees maybe of rake because of how it was made and how it's brazed on. Now this is not a very robust tool, but for some materials this would work really great. The problem with a tool like this is that it's fragile. This edge is fragile. 50 years ago, when I was a kid grinding carbide in the machine shop, the rule of thumb was that you couldn't use more than 7 degrees rake on a carbide tool. So here we are all these decades later with better carbide alloys and quite a lot. Maybe this is 3 times that 7 degrees. I don't know how well that works. Doesn't look like I've used it much, but anyway, that's an extreme example. Much more common is a cutter like this, which has 0 rake. And again, the 0 rake cutting tool design isn't normally what you would want for wood at all, because it's a scraping cut, not a slicing cut. And so looking here at the Salstrom cutter, I just played around with this and figured out that the rake on the side of this tool is a little more than 35 degrees, which is a huge amount of rake, and it's why this tool works so well. And it's something that you couldn't accomplish. You couldn't make this tool out of carbide. There's just no way that it would stand up to the forces. This is the strength of using a steel tool for a job like this, because it has a little bit of resilience and elasticity, so that when the cutter is shaking and vibrating a little bit, it can withstand those movements and forces and not crack off. So that's the big advantage of using high-speed steel. This is M42 steel, a very common alloy. This may be M42 also, who knows. It's quite commonly used for all kinds of modern cutting tools in the machine shop and the wood shop. Fantastic alloy. Whole different animal. That's a scoop, as far as I can tell you. Carbide is a wonderful asset. Sometimes we just wouldn't want to do without it. And in other places, it just can't hope to provide the kind of tool shape, the tool geometry that we need to get a really nice cut in a piece of wood that we care about very, very much. All right, that's my take on carbide and high-speed steel.